let's suppose this space represents some space you're interested in. I always get mad when students don't label their axes, so let's label our axes. I guess we better pick a problem first. What problem should we solve with KNN? Do a classification problem. Let's do the tastiness of pizza. Sound good? How about meatiness? Pizzas can vary in their meatiness, right? And pizzas can also vary in their what? Breadiness. So how about their carbiness? Okay. Now, all right. Let's use.
Like everything in the right-hand top corner.
So I'm going to say in general, if you give me a random pizza that's loaded with high gluten flour, thick bready crust, and it's just covered in meat, I can imagine a good pizza up there, right? In fact, I can imagine quite a few good pizzas up there. So let's say that there's one that's good, and there's one that's good, and there's one that's good. Although, you know, there's got to be one. So I went to Taiwan for a couple of years, and I had some pizzas that were covered with corn. And actually, corn surprisingly wasn't that bad. But there were I had some squid pizzas and some, can you imagine a carby and meaty pizza that isn't tasty?
Stale one.
A stale one, there you go. Rotten cheese. Okay, how about a blue cheese fish pizza? Yeah, I mean, come on, there are some bad pizzas that are meaty and carby. There's a thin crust vegetarian pizza. Is anybody like that? I hope not. We're gonna, don't raise your hand. No. Okay, we better put a good one down there, and maybe it's all on voting. And you know, I've had some good thin crust pizzas. I have to admit it. It just, I don't know if I'd call it a pizza. They were good, but they just weren't. Whatever. Does this space sort of represent your?
Could represent someone.
Someone? Okay, great. Well, these are the data points that we have because we have only eaten a finite number of pizzas in our finitely limited lives. And now we want to ask the big question, what about this pizza? No, that's a dumb question. What about this pizza? Okay. How is this pizza going to be? And why are we asking this question? I don't know. Maybe Rosie the robot's going to make a pizza and she doesn't have enough gluten to add to the flour to make it get all the way over here, but she has just enough to get over here. And she only has access to this much meat without going to the store and is trying to decide, should I order from Amazon Prime prior to making this pizza? Or should I just start making it? Queries this, and if it ends up being a smiley face, she'll make it, and if it is frowny face, she won't make it. You can see how this could be a component in an AI system, right? Okay, well, let us ask the question. If we find the nearest neighbor to this point, it's that one, it's a smiley face, therefore we are a smiley face. Rosie should begin making the pizza. Did you get KNN? Stupid, easy learning algorithm, isn't it? In fact, it doesn't even really learn, it's just rote memory. The data set itself is the knowledge. And because this data exists, you can use it to make classification decisions. There's another type of nearest neighbor called 2NN. So what we just did was 1NN. We found the one nearest neighbor, and we assumed that the point we're classifying has the same class as its nearest neighbor. If we find 2NN, we're going to find the two nearest neighbors, which are this one and that one. And guess what? They're both smiley faces, so obviously this one's a smiley face. What if we do 3NN? 1, 2, 3. 2 is more than 1. I say it's still going to be a smiley face, right? 4NN, 5NN, 6NN. And what's the next one? Okay, so what's the class of this? Yeah, so excellent observation. It depends on the algorithm. How do you do it? And if your algorithm is count up the neighbors and vote, and they all get equal vote, then, well, this one's a problem. You're going to be, I guess we'll draw a horizontal line and say you are moderately. It's the have a day face. although sometimes you can't average between your classes. So this is all problem specific, and yes, you can do whatever you want. There are no rules. There's another thing you can do, is weight your voters by their distance. It turns out if you weight them by 1 over d, that ends up being equivalent to linear interpolation in single-dimensional problems. Let me illustrate with a number line. If this one goes here and this one goes here, and you're asking about this point, how far are we from this point? That far. How far are we from this point? That far. If we weight 1 over that distance times this height plus 1 over that distance times that height, and then divide by the total 1 over the distances, 1 over this distance plus 1 over that distance, and average them, it will come out to that height such that if you drew a straight line from there to there, it will cross that line. And so it has been argued that, hey, we like linear interpolation, therefore weighting by 1 over the distance, the Euclidean distance to all your neighbors, kind of seems like it makes sense. Right? Okay. I tend to like that approach. It's probably more common to just use equal voting and just not use too large of a k. By the way, for reasons of convention, we almost always use the letter k to represent the number of neighbors. There's no reason you have to. It's just what a lot of people do. Yeah.
Could we just make sure k is odd?
Yeah, so truthfully, that's the most common solution. It just always pick an odd k, do 1nn, 3nn, 5nn, 7nn, etc. And as long as it's always odd, you're always going to break the tie, and you'll always get an answer that you like.
There's also only 2 different possibilities.
That is, yeah. Well, let's suppose there are 3 possibilities. We'll make, I don't know, magical pizzas? They make you really happy for a while, and then afterwards leave you slammed and late for class. And
I accept these conditions.
okay, I shouldn't do things like that. We do not endorse drugs in this school. Don't do drugs, it's bad. I'm actually serious about that. Did you know your brain's made out of chemicals? Guess what drugs are made out of? Chemicals. You think you can handle it? You're wrong. Humans can't. The chemicals make you think you're doing just fine, and in fact you're not. So seriously, don't do drugs. Okay. Having said all of that, yeah, I like to weight by 1 over the distance. It's kind of like linear interpolation. Can you do that with 3 different classes? Yeah, it just doesn't, it's not really accurate to say it's linear interpolation anymore, but because it is with 2 classes, we kind of just say it is. So you could still weight by 1 over d with however many classes you get, and it's very unlikely that you'll end up with totally equal vote because now we're in continuous space, right? Now, it's still possible they have equal voting. What do you do in that case? Usually you'll just be arbitrary because you say it happens so infrequently that who cares? It'll happen 1 time ever. It's not even worth a line of code to solve. Yeah, I guess a statistician would say no, you should roll a dice and exactly
you could just
that.
roll the probability.
You could do that. There's a lot of things you could do. It's also very common, for whatever reason, to weight by 1 over the distance squared. What do you feel like that's going to do?
Favor the Postman animal.
Yeah, if we come back to this domain, it's going to be kind of you see how it kind of says, hey, the one you're closer to carries a little more weight than the one you're farther away from. Doesn't that just kind of feel more like the right thing to do to you? I kind of like that. It makes sense. So, hey, 1 over distance squared might be an even better way to do it. Well, for that matter, why not 1 over distance raised to the infinity power? I mean, you might as well ratchet that 2 up or down to any number you want. 1 over d to the mth power, and then you could tune m until you get your optimize your results, right? That's one thing you can do. So, yeah, 1 over d to the some variable. I guess d to the p for power. Yep. So there's an equation for the weighting, if you like. And then what's the optimal value of p? There are some arguments that 2 is the optimal value. And there's also some arguments that it's not. And so you can do what you want. You could tune it. Let's ask about that. What is the best value for k? Is it going to be 1? Is it going to be n? Well, here, I made a little program here. There is a little tiny picture in this corner, and it's a rather famous picture. And if we take all the pixels in this image as data points, and then we come to this great big black field here, and I spread those pixels evenly around this field, it's kind of like I have all these points where I know the color of the pixel, right? And I'm going to use k and n to interpolate the values in between them. Does that make sense? Okay, if I use 1 and n, here's what I get. Kind of obvious, right? Because it makes little squares, because at each point you go to where the nearest data point is to choose what its nearest neighbor value is. Where are the points of data in this picture? Are they at the corners? No, they're right in the dead center of all the squares, right? Because that's when that point becomes the closest neighbor relative to the other neighbor. Okay, if we use 2 and n with equal weighting, meaning they're just doing maximum vote, there's what you get, right? Okay, if we use 2 and n with linear weighting, it becomes a little more blurry. You have to kind of look closer. So there's still the same diamond-shaped things that you saw before, because in those diamonds you still have the same 2 nearest neighbors, but now every diamond has a gradient in it. Makes sense, right? 4 and n with equal weighting, now it's kind of little circle-y things. 4 and n with linear weighting, now they're gradient-y circles. 8 and n with linear weighting. Now you see how it's starting to get kind of blurry? Is that better or worse? I don't know. If we went to 32 and n, it would start getting this blurry mess. Could that ever be better? Sure, if you had really noisy data, in this case I have pristine, not noisy data because it's a nice clean picture painted by somebody. But anyway, it seems to do a nice, decent job. Interestingly, let's do the neural net for a little while. Oh, it crashes, dang it. Okay, my code's a little out of date. Oh, for the heck of it, let's do a decision tree with random divisions. Kind of interesting, isn't it? Here's orthogonal decision, or what are they called? Perceptron decision trees. Here's a bagging ensemble of 30 decision trees. That looks pretty nice, doesn't it? Okay, here's a bagging ensemble of orthonormal decision trees. This is my favorite one. I think it looks really clean. Looks kind of like some impressionistic, artistic thing. Unfortunately, my neural net crashes. If we were to do my neural net, I usually do that in my other class because when I teach neural networks, what you see is these blobs form as it slowly fits to the data and starts to fit out a shape. What's interesting though is it never looks this nice. And people usually get the impression of, hey, neural nets are lame. What's going on? Well, the difference is that neural network has something like 2,000 weights in it. And those are the number of things it's tuning to fit the image. And because I don't have enough weights, it's kind of blurry. Neural nets are also very slow. But this KNN model has all of the data points themselves. The model is hundreds of times bigger than the neural network. And because it's a lot bigger a model, it makes a much crisper picture. Yeah. Well, I actually do it in real time, so you watch it kind of form as it's training. Unfortunately, my code's broken right now. Sorry, I should have tested that before class. I didn't even think of demoing it for you. Anyway, basically, do you get KNN? Fabulous. I'm almost done with this section. Now we can move on to unsupervised learning. Few other topics we need to cover, though, are things like distance metrics, such as Mahalanobis distance and some other things. I'm going to be pointing you at a little book I wrote. Because I wrote it, and I was in a hurry and I haven't had time to polish it, it's not great. Don't be reading it word for word as though it's some kind of really well-written book. Read it as though it's a reference manual. Skim through it, and when you don't know something, then read it in detail. I was hoping that would just pop up, but our internet's being slow. There's a lot of topics there I'm going to kind of go through, and it'd be good for you to take a look at it. But I'm out of time, so thanks for coming, and we'll talk more about KNN next time.